Welcome everyone, and this is your first tutorial in the Forces module. Okay, here we go. Oh, by the way, I'm Jim Corkins. So let me show you how to do these. All right. So the intent here, which is to help you with your creating of force diagrams. So you're going to learn to create force diagrams based off of a description, and you're going to list out the velocity and acceleration vectors in the x and y direction, or what they probably should be, what is causing the force, so what's causing the force, and what you're going to name it right here, and what direction it's pointing at. So doing all this based off of this description in this picture, then you're going to create your force diagrams. Okay, so here we go. So we're going to list all of the contact forces and non-contact forces. All right. Well, the only non-contact force, I always start with this, is mg, which is the weight of, in this case, the textbook. So this textbook is being pushed to the right with a force and speeds it up to the right along a frictionless surface. So this physics textbook has a weight to it, and that's the non-contact force, mg. mg is always pointed straight down towards the bottom of the page, in this case in the negative y direction, unless your coordinate system is twisted, but we're not doing that right now. So we're going to just label this force. Actually, what I'm going to do is go back here. This is the weight of the object, pointing in the negative y direction, and we're going to subscript this mg. So this is what you're supposed to do for this. Okay. What else is physically touching? So now we've got the non-contact force out of the way. Let's look at what is physically touching the textbook. I see a hand and a surface. Okay, so the hand, I'm going to use black, is touching it, and it says it's pushing it to the right, so that's in the positive x direction. And so I'm going to subscript this. Here's going to be my force vector. I'm going to subscript this with h. So you don't have to write out the full hand force. You can if you want to, but you want these to be brief. So the hand force, F sub h. Okay, now the surface. The surface is, so it's on the surface, it's holding up the object. So I'm going to call this surface. And since there is no friction or resistance to this, it's just holding up the object, because they said this is frictionless. And so that is going to be called the normal force. When we're dealing with surfaces, we call them normal forces. All right, let's indicate the velocity vectors and acceleration vectors as positive, negative, or zero. So they said it is speeding up as it's moving to the right. So if you're pushing something and it's speeding up to the right, both of those acceleration vectors and velocity vectors will be positive. And whenever I've pushed a book to the right, it's not speeding up in the y direction, and it's not accelerating in the y direction. So you could assume that is true. Now that we have this all filled out, let's go ahead and copy these vectors over here. Now, since this is pointing in the negative y direction, I'm going to make this negative. I'm going to make this force positive, since it's pointing in the positive x direction. And I'm going to make this a positive. And I'm just going to copy these vectors right over to our force diagram. I always put the tail of my vector to the dot and have the vector heads pointing away from the dot. So in this case, the non-contact force is the weight of the textbook. The earth and the textbook physically don't have to touch each other for the earth to pull down on the textbook. So that vector is pointing straight down. And we're going to label that negative mg. All right. Let's do this force is pointing in the positive x direction. So I'm going to make it pointed to the right. And let's try making that vector straight. And that's positive f sub h. You don't have to put the vector heads on this. I do because I'm probably detailed oriented. And the normal force is pointing in the positive y direction, we've said. And that is the first couple problems on this tutorial. Okay? Now, what you're supposed to learn from this is, given a brief description and a picture, is to create all of these things, to figure out what the non-contact force and contact forces are and their directions, figure out the velocity vectors and acceleration vector directions, and create your first force diagram. Okay. From here, what we would do is we'd create x direction equations and y direction equations, similar to what we learned in the 2.1 trigonometry review tutorial. However, the other tutorials are going to help us with this part. Okay? Let's move on to our next type. So over here, this is what I was just talking about. Now we are given a force diagram, and we are supposed to create we're supposed to sum the forces in the x direction and y direction, and from this, make a guess as to the directions of the velocity vectors and acceleration vectors, both in the x and y directions. And then we're supposed to answer these as numbers right here. So we're supposed to figure out the mass of the object, the acceleration in the x and y direction, and the direction of the velocity vectors and acceleration vectors. So let's go ahead and try this out. So what we learned from 2.1, whenever you're given vectors, try to create your coordinate system. So we're going to do that. This is pointing to, this is positive x, this is positive y, this is negative x, and this is negative y. So the first thing we're supposed to do is try to calculate the mass of the object, given that g is equal to 10. Well, the weight here, is 6 newtons. So 6 newtons is the weight of the object. That is equal to mass times gravity, which in this case is mass times 10 meters per second squared. So right here, we could see that 6 newtons divided by 10 meters per second squared is going to be the mass of the object, which is going to be 0.6 kilograms. So this is going to be 0.6 kilograms. All right. Now, this is pointing in the negative y direction, so I'm going to kind of rewrite this, and I like to use mg. So mg is pointing down, and that's going to be negative 6 newtons, as it's pointing in the negative y direction. The normal force, which that's weird that there's a normal force pointing down. My guess is there's probably some type of ceiling here, and you've thrown a ball, it's hit the ceiling, and for the moment that it's touching the ceiling is pushing down on it as the earth pulls it down. So that's what my guess is what's happening here. So this normal force, which I'm going to use blue as my surface force, is pointing down. So that's F sub n, and that's in the negative direction as well. Okay. Now, we are supposed to copy these forces over to here, and since we have no x direction forces, this is just 0, which is going to then be equal to our 0.6 kilograms. Whenever you sum up forces, you sum up the forces. Here, I'll briefly show you what I'm talking about. Whenever you sum up the forces, we sum them up and then set them equal to mass times acceleration in the x direction. Okay. However, there are no forces in the x direction. So when we set that sum of forces in the x direction to be equal to the mass of the object times the acceleration of the object in the x direction, that's going to produce an acceleration in the x direction that is equal to 0. Because 0 divided by 0.6 kilograms is equal to 0. Right? So I'm setting these things equal to the mass times their acceleration. And since this is the x direction forces, this will be the x direction acceleration. All right. So we can see in the x direction, it's not going to be moving or accelerating. Okay. So the x direction velocity is going to be 0, and the x direction acceleration is going to be 0. In the y direction, that's a little bit more subjective, I think. All right, well, let's go ahead and sum our forces. And you don't have to write this out formally like this, but I am. I have a negative normal force pointing down and an mg force pointed downwards as well. And then we're going to set those equal to the mass, which we figured out, which is 0.6 kilograms times the acceleration in the y direction. So if we put in our numbers, which that negative normal force is negative 2 newtons, and the mass, well, the weight is negative 6 newtons, that's going to be equal to 0.6 kilograms times the acceleration in the y direction. So adding those two things up, we're going to get negative 8 newtons, which is going to be equal to 0.6 kilograms times the acceleration in the y direction. So negative 8 newtons divided by 0.6 kilograms. That is going to be equal to our acceleration, which is going to be equal to, I do not know, negative 8. So we're going to make that, just write 8 and make it negative. We're going to divide it by 0.6. That is equal to negative 13.3333 repeating. So that acceleration is going to be down. And meters per second squared. So this is going to be negative 13.33 right there. My guess is velocity is also going to be in the negative y direction, although it could be one of these two. So it could be 0 for that instance, and it could be the negative. It's an unknown, really, because we don't have a friction vector, like a kinetic friction vector. We cannot be sure which direction it's actually moving. So we don't know what the velocity vector in the y direction is. So you could actually choose to put a question mark there. You need to know the direction of the kinetic friction vector in order to figure out the direction of the velocity vector. Kinetic friction is always pointed opposite the direction of the velocity. Okay? Static friction can be pointed in the same direction as the acceleration vector, and most of the time it is, but not necessarily the velocity vector. Okay? All right. So that is your introduction to 4.1 tutorial. Okay. I hope you learn a lot from it. Okay. It takes you through the steps of creating your force diagram, and then once you have a force diagram, what do you do with that? Okay. Have a good day. Bye.